Well, good morning, folks.
Morning.
How are you all doing today?
Good.
Good.
Oh, you moved 9.2?
Just a couple days.
That's awesome. Thank you.
Just in case it'd be helpful. So, where's the thing I'm looking for? There it is. Okay. And I put on that quiz. It didn't work when I put it in on Monday. So I left that open an extra day or so. So this quiz that's listed due on Friday, it's like 5 questions. You got like 90 minutes, which is way more time than you need. It's set up a little bit like a test, but more like the homework. So you can actually do the questions a couple of different times. So really it's just kind of like a practice. Here's some stuff to practice with and kind of grow with that I can then add to your test scores from last time just to kind of boost those a bit.
Thank you.
Sure.
Thank you so much.
So make sure you find some time to do that over the next couple of days. It does have, I think, a couple things from 7, one thing from 6, and actually I think has one from 8. So it's just kind of, hey, here's some stuff that we've been doing to kind of practice with. Let's see, we have been talking about 9. We want to talk about 9.2 today. We talked a little bit at the end last time about the differences in 9.2, the idea of changing those critical values from z-scores to t-scores to account for the error brought in by using the sample standard deviation. So we'll look at how to find the appropriate t-scores today, probably mostly by hand. But before we do that, is there anything from 9.1 that you guys wanted to ask about that we could clarify to make sure we're happy with that before we move on? Because really, the better we understand 9.1, the easier 9.2 it is going to be, because it's very similar.
If it doesn't take too long, could we look at the critical? Sorry, what is it called?
What's that, David?
This tables and formulas, the tables2.pdf, that little normal distribution. I think it's the critical values handout.
Gotcha.
I've been trying to read it. I keep getting it wrong.
See, what that was under one of the weeks, wasn't it?
I think it was for chapter 9, I hope, unless I'm looking at the wrong thing.
No, that's the hypotenuse handout.
That was week 8.
The confidence intervals sample size handout?
The one just below that, tables2.pdf.
Ah, the tables one. So this document.
Yeah.
So these kind of those e-score table we worked with, right?
Right.
So that one you're happy with, right?
I think that I've been looking at the wrong thing, actually.
Well, because there are 4 different tables on this paper.
Right.
There's the z-score table, which is that table of areas from chapter 7.
Right. I guess what I've been trying to answer and getting wrong is actually number 1 in 9.1, that homework. Just asking for, the critical value from a confidence level.
Right.
So I think I'm looking at the wrong thing.
Well, that would be this piece down here.
Right.
For these particular confidence levels. But if it's not one of those, we've got to find it with that middle value process. And that middle value process, you can use the norm inverse for, or you can use this big table for. So that would work. Did
Yeah,
you want to look at one of those?
I've been getting it like really wrong.
Like really, really wrong?
Like really wrong. Like close to a whole point off. Like
Okay.
if the answer is 1.3, I'll get 0.3 for some reason or something weird like that.
Okay.
So the one I'm looking at is asking for a critical value from a confidence level of 96%.
Okay. So let's do that and see what happens. There's usually a couple of reasons why, so we'll try to find it. So you said 96%?
Yeah.
Okay. So you know me, the first thing I'm going to do is draw a diagram, right? With the middle 96%. And you could write that as 0.96 if you wanted to. That's centered around some mu, right? And has a standard deviation. Now, if you're looking for the z-score, that mu is presumed to be 0, and the standard deviation is presumed to be 1, because z-scores live in the standard normal, right? Okay. So if we want this 96%, if we want these bounds z1 and z2, one for the middle 96%, one big observation should be that these values should be symmetric, right? So, you know, if this was 1.7 or negative 1.7, this one would be 1.7, right? You happy with that, David?
Yes, sorry, I nodded.
Okay. So really, we only need to find one of them. If we find one of them, we know the other one. Fair? Now, the big issue with finding them is that 96%, we're not really going to use that 96% directly. We have to use that 96% to figure out what value we need, because our tools want to tell us or want to talk about cumulative values from kind of the negative infinity to some location, right? So we got to figure out for that 96%, centered 96%, how much is this tail going to be? And how do we do that? Well, we know there's 100% in the whole thing, minus the 96% gives us how much percent is on the outside. And there's half of that in each tail. So there are 2% there. Fair? So what we've got to use to figure out what, excuse me, what that z-score is that 2%. Now that 2% is naturally going to give us the negative 1, right? If we wanted to instead find the positive 1, we could do that as well, but that would be this big piece from z2 all the way down, right? And the z2 all the way down is the 96% plus this other 2%. So that would be 98%. So those z values are going to be based on the 98% and the 2%, not directly based on that 96%. You happy with that so far, David?
Yeah.
Is that what you've been doing?
I was actually looking at the table but this is probably going to be easier because that
Well-
table is a little. I find it a little janky.
At this point, we could jump to the janky table because we're looking for 2%, right? So 2% is 0.02. And we could look on this table for where 0.02 is. Can I zoom in on that at all? Oh, my goodness. Because my eyes were going to go. So we'd have to look. Now, it would have to be in the field somewhere, because that 0.02 is an area, right? And that's 0.00 almost 2. We want 0.2 or 0.02. So 0.02, 0.02, where's this close? These two are pretty close, right? That one's off by 0.0003. This one's off by 0.0002. So this one's probably the closest one. Fair?
Yeah.
So that would be an approximate z-score of negative 2.5. Fair?
Mhm.
So negative negative 2.05. So from the table, from the Z table, it would be negative 2.05. Now, if we wanted to use instead the calculator and get one that's a little bit more precise, if we wanted that, we could use the inverse norm tool and find that 0.02 with a mean of 0 and a standard deviation of 1. And that should output the same value up to some rounding. Fair?
Yeah, I think I know exactly what I was doing wrong. I
What were
wasn't
you doing wrong?
accounting for the total from negative infinity up to the second z-score. I was just doing the
Just
middle
putting
value.
in that 96.
Yeah.
Yeah, and that's the usual thing that folks do. They use that 96, not that 98. And that's one of the reasons I actually tend to encourage use this too. Because if you're using that too, you're having to think the right way. If you focus on finding that larger one, it's easy to accidentally swap those. And that makes the values usually not horrifyingly off, but off enough and significantly off. The larger the percentage too, the less off it'll be. If you want like the middle 20%, your value is going to be way off. The middle 96% versus 98%, it's not going to seem as dramatic, but they're always going to be at least that little bit wrong. What do we got? I'm just curious how close that is to the value on the table. Should be really close, but the table is more of an approximation because we had to use that 0.0202 value, and it's rounding quite a bit more. But if we go to that inverse norm 0.02 or the 0.98, either one, yeah, we get negative 2.0537489111 and so on. So that even rounds to exactly the same value. Now, this so far is essentially chapter 7 skill, right? We did a bunch of those in chapter 7. The big thing in chapter 9 asks instead of asking, what are the z-scores for that middle 96%, it asks what is the critical value for a 96% confidence interval. Well, that critical value is how many z-scores do we have to go out to figure out, or how many standard errors do we have to go out to make sure we're centering 96%? Well, that is the same as that value, the absolute value of that. So the critical value is 2.05 and as many decimals as we want. So now we're just giving that, that z-score that we practiced finding, we're going to be using it for a tool, and that tool is critical value. And it's really common for people to get fairly good at this in chapter 7. And then chapter 9 comes along and it's being asked in a slightly different way. And it takes a while to have this skill translate to that behavior. Yeah. That this is really that same question. It's just worded differently. How might we use that? Say we find a sample of, let's say 110 people, of which, let's say 35 are what? I don't even know. 35 are special in some way. Doesn't matter what way. 35 are special. Find a 96% confidence interval for the proportion of the population that is special in this way. Well, we have a sample size, 110. We have a sample proportion. Our sample proportion is the 35 of the 110, right? We want a confidence interval or a confidence level of 96%, and that implies a critical value of 2.05. We know that because we just found it. If it wasn't that unusual of a critical value, if it was a more common critical value, it would have been on our table, right? Where was it? Down here. For the confidence levels of 90, 95, 98, 99, those are so often used that we just have a table of them. But where do these numbers, these critical values come from? Well, those critical values come from this exact process we did up here. Even notice that symbol, it's hard to read here, but that's Z alpha divided by 2. So the amount of error in a 96% confidence interval, the amount of error is 4%. That 4% divided by 2 is 2%. So that alpha divided by 2 is this process. Okay. So yeah, if it was one of our more standard values, we wouldn't have to do that to find it. We would just look it up, which is why it's nice that we have, this chart. And we could add to this chart. You could add to this chart 0.96 and write 2.05. Okay, now we'd have a new one on our chart. We'd never have to calculate again. If you want a chart of all of them, there you go. That's what this big Z-score chart is, right? Sort of. So how do we find a confidence interval? Just to remind us, our confidence interval is our point estimate plus or minus our critical value times our standard error. So our point estimate would be the 35/110ths plus or minus our critical value times our standard error. And because we're a distribution of proportions, that is the square root of, sorry, I'm writing this small, P times Q, which is 1 minus P. So that's 75 out of 110 over 110. I'm going to mark that just for reference. That's standard error for proportions. That's square root of P, 1 minus P over N. And you could probably, write it in decimal form instead if you wanted to. Or I'm not going to calculate that out, but and I do like to remind us that, before we had situations where we had, say the mean was 5 and the standard deviation was, say, 3, and you were asked to find things like usual range of values, right? What did you do to find the usual range of values? Well, you took your sample and you add or subtracted 2 standard deviations, because 2 standard deviations was usual, right? Same process, basically, except instead of 2, we've got a critical value dependent on a confidence level. But we're still taking a center and adding a number of standard deviations. Fair? It's just that number of standard deviations is dependent on our critical value. And instead of standard deviations, we're using standard errors because we're in the sampling distribution. So David, that went a little beyond the scope of your question, but why we want to find the answer to questions like that is so we can then go on and find confidence levels for it. And this is also why in chapter 7, we did this question a fair number of times in chapter 7, so we would know and understand where these values come from.
I just psyched myself out because the words are different.
Yeah. And that's that, they are. They are. 7 or 8 in 9-1, they're pretty much the same question. Don't trouble with them. Okay.
I have a question.
Yes, ma'am.
In the question 14 from 9.1, I got twice 2 decimals, 2 numbers below. Like the correct answer for me was 188, and I got 186.77, and I don't know why it happened twice. Like 2 numbers below, I got the answer from 2 numbers below. Do you understand that?
Yeah, I'm not sure why that would be. Well, we can look at it. Let's look at
Yes, please.
7 or 8 first, though, and then we'll look at 14, you said? Yes, 14?
Yes,
Okay.
sorry, my internet cut off.
No problem. So I'm going to grab 7, and I'm going to put it over here so I can write on it instead of just point at it. But yeah, after we look at those two, we'll start looking at 9.2, make sure we look at it. But again, a lot of the logic in 9.2 is very, very similar. So, and there's a reason they do 9.2 first, is because it has one less issue in them. So the more comfortable we can be with 9.1, the easier 9.2 will go.
I don't think that was the question because
No,
I
this
did
is number 7. I'm going to do that first,
sorry,
and then
sorry.
14. No problem. Okay, so actually, let me give you guys 2 or 3 minutes and try to answer what your answer to this would look like. So take a minute or 2 and do this. And
Can you make that bigger, please?
Yes. And in case it helps, there's your, in case you guys haven't printed out one of those charts yet. It's in your textbook too. And I'll certainly find it. So while we are only in this class finding confidence intervals for either means or proportions, It's the only two that we're doing in this class. You can find confidence intervals, as I've mentioned before, for lots of different types of things. But no matter what they are, all confidence intervals are built the same way. All confidence intervals are an estimation. Estimation. I don't know how to spell estimation, but that is my estimation of spelling estimation. An estimation plus or minus a margin of error. That is all confidence intervals, no matter what they happen to be of. And that margin of error can be more broken down into an estimation plus or minus some critical value times standard error. Where that critical value has to do with, or that critical value is dependent on the confidence level you want. So this is true for any confidence interval of anything. So it's almost whenever you see or hear the word confidence interval, estimation plus or minus margin of error. Better yet, estimation plus or minus critical value times standard error. So that's always. Now, because this is a proportion problem, essentially a binomial problem, our estimation is going to be a sample proportion. Good old p hat. Not p because p is the true proportion, p hat because it's a sample proportion. I think your book likes p star sometimes. I've seen some places go p apostrophe. But some sample proportion. Standard error for binomial, for proportions, is, they often use sigma p, is that square root of p times q over n. And the critical values are z-scores. So that is specific to proportions. It's the type of estimate, the type of critical value, and the type of standard error. So that estimation is going to be some sample proportion plus or minus a critical value, which is going to be a z-score. And David, like we were talking about, that's the notation they use, z of alpha divided by 2. So that z-score of half the error, and that's what's on those tables, times the standard error, that's square root of p q over n. So all we have to do is find, essentially in this problem, find those three things. P, in this case, p hat, the critical value, and the sample size. If we have those three things, we just got to put them in the right place. Okay? So in this particular question, we have a sample size of the 200. We're given that pretty directly. Out of 200 people sampled. Okay, That's our sample size. 126 had kids. Well, that is a slightly subtle version of giving us our sample proportion. We're not told the percentage of people that had kids. We're told the raw value of 126 out of 200 that had kids. And that often throws people off. Savannah, I'm not sure if that's what threw you off or not, but it's often a little tough because we're not given proportional information, but we're asked for proportional information. So we have to build that proportion. Yeah. So we have to build the, what's this, 0.63 proportion. Cool. And then the critical value. We had for 99%, again, we could build it like we did for the 96, but since 99 is one of the standards, we can just look it up, 2.575, so 2.575. Now you could also say we need that Q, but that Q is derived from the P. That Q is just 1 minus P. So that's the 0.37. Then we have everything. So then our confidence interval is the point estimate, the single estimate, plus or minus the z-score, the 2.575 times the standard error. It's often handy to find the standard error off to the side and then plug it in, as opposed to trying to type all this in it. Like all this in as one statement into the calculator. So if you want to go off and find standard error separately, that can actually be really handy. But we end up with that 0.63 times 0.37 all over the 200 for computing our standard error. So yeah, it can be handy to go off to the side and find that standard error first and then just plug it in. As long as you're carrying enough decimals of accuracy, you'll be fine. Now, we did talk yesterday or near the end about the issue of this P and Q isn't supposed to be the sample proportion. That P and Q is supposed to be the true proportion. But we don't know the true proportion, so we use the sample proportion instead. If you're for some reason working with a scenario where you happen to know the true proportion, but you still want to do this, you should use the true proportion instead. But generally we don't have it, so we use the sample proportions instead. And for proportions, that doesn't cause a problem because the sample proportions and the true proportions are usually sufficiently close. So it just doesn't bring in a lot of error. But as we talked about at the end yesterday, when we go to doing distributions of means, it's not going to be close enough to use our sample values. So we'll have to compensate for it. But we'll talk about that in a second. So yeah, again, so Savannah, you asked this, usually the biggest issue with these is the fact that you've been given the information in a slightly, in not the form you want it in. So it does require that extra step and that extra wait a minute, where's my proportion coming from? You guys want to compare answers you got for this? Or are you happy with that process?
I got 3.89
For what?
for all of it.
For the whole thing?
Oh, yeah. Why? Yeah. Why is there supposed to be two answers?
Well, one for the plus and one for the minus.
Oh, yeah.
I got for the lower end 0.54 through, I guess 542. And for the upper end, 0.718.
That's what we got too.
Okay. And that seems fairly reasonable. That's a pretty wide range, but 99% confidence intervals give you pretty wide ranges. So
I can. Can you do the step by step after we get the answer from the equation to the plus and minus? Please.
yeah. So I'm just going to find the square root of the 0.63 times 0.37 divided by 200. Make sure I type that in right. And so that I got 0.03414. And then that gives us, so that's our standard error. If I multiply that by 2.575, that gives us a margin of error, the product there, of 0.08791. So that's the plus or minus that I'm finding.
Yeah, I found what I was doing wrong. I was writing 0.63 equals 2.57.
Ah, gotcha.
Yeah. Thank you.
Sure. So that does mean another way to say this, as opposed to saying it as an interval, we could also say our true proportion we think is 0.63, and plus or minus the 0.0. I'm just going to say 879. So, that's a perfectly reasonable way to express that. You often see in practical applications, you'll see that and margin of error. It's nice to look at it as an interval, but we often see it this way. One of the things that often bothers stats people is what you often see is this. You'll often see the proportion is this, and then somebody will write very small off to the side, as if it doesn't matter what the plus or minus is. No, that plus or minus matters a lot. That's a big deal. We have no reason to believe it's closer, and this is fairly important. We have no reason to think it's closer to the 0.63 than it is to the 0.71 than it is to the 0.54. Fair? It's just as likely that this proportion is 70% as it is that it's 63%, as it is that it's 55%. All of those things are equally likely. There's a prejudice towards the center of our approximation, that prejudice has no basis. There's no more reason for us to think it's 63 than 58. Okay. So yeah, whenever I see this, I always cringe. And that's one of the reasons why confidence intervals are in some ways preferred, because it tells you, okay, it's somewhere in this range. It makes the low, the bottom of the range and the top of the range the important part, as opposed to, even when you write it like this, it makes that 63 sound more like it's somehow more significant. Yeah. All right. So then you wanted to look at 14, and then I want to talk about, we'll try to do 14 fairly quick, and then we'll talk about, what was it? Oh yeah, 92. Where'd 14 go? Oh, there it is. So I do want to do this one a little quicker, but I am still going to give you 2 minutes to decide what you want it to be. So I'll give you till 12:30. Good old sample size questions. We talked yesterday about doing this either from solving or from the little formula they give you, right? I'm going to do it from the solving perspective, but I will remind you that they do give you a little formula for it. Okay. So again, as soon as we start talking about confidence levels, we're essentially sort of talking about confidence intervals. Confidence intervals, again, are your estimate plus or minus your margin of error. In this particular problem, though, we're not actually asked to build a confidence level. We just want to make sure we end up with a particular margin of error. So we're going to be focusing on that margin of error. And we want that margin of error to be less than or equal to 9%. Right? So what we're essentially going to do is take that 9% and set that equal to our margin of error. And then any sample size that makes it equal, anything bigger than that will make it less than or equal to. So we don't have to solve the, though you could leave that as less than or equal to the whole time if you wanted to. So again, margin of error, how do we find margin of error? Margin of error is our critical value multiplied by our standard error. Because this is a problem in proportions, that critical value is a z-score, and the standard error is that square root of PQ over N. Fair? But again, I'm going to remind you, this is because this is a proportion problem. If it is not a proportion problem, the critical value isn't a z anymore, it's a t. We'll talk about those in a minute. And the standard error isn't the square root of PQ over N, it's the standard deviation divided by the square root of the sample size, just like it was in chapter 8. So those two things change depending on what world we're in, whether we're in the proportion world or the means world. Now for a 95% confidence level, if you look on your chart, that associates with a critical value of 1.96. 95% critical value 1.96. So great, we have that piece. 1.96. Still supposed to equal 0.09. Now, the trouble is we don't know a sample proportion, and we certainly don't know the population proportion. So I'd like to be able to put in either a sample proportion or a true population proportion into that, but we're not told what, or we're not told any idea of what our proportion might be. So what did we have to do in that situation?
Assume the proportion was 0.5 or 50%.
Assume it was 50%, yeah. And you know, in this particular question, and this is probably why they chose this particular metaphor, when you're talking about a political candidate, you're looking for that who has above 50%, right? So political candidates, you're often worried about that kind of 50, it's almost 50-50 case anyway, fair? But even if it's not political candidates, 50-50 is the default unless you know otherwise. Because 50-50 requires the largest sample size. So if you don't have any reason to think it's better, you go with 50-50. Oftentimes I've seen people try to use that 0.9 because they're looking for some proportion, and that's the only proportion in the problem. So they'll use that 0.9 as a p. It's not a p, it's the margin of error. So we got to be careful. But you know, if you're looking for, I need a proportion, and that's the only one I see, I get that. But we do have that default of 0.5. Divided by the sample size that we don't know. So then solve for that end. We also did talk about the formula. What was it, if I can remember? Because I don't do it this way. I just find it. What would it be? I think it's the critical value divided by the margin of error squared times p times 1 minus p or q. So you could plug them into that, but you get that by solving this. You know, divide both sides by the 1.96. Multiply those together, 0.25 over n. Square both sides, 0.09 over 0.96 squared equals 0.25 over n. Flip both of those just to make your solving easier. 0.96. And frankly, anytime you're trying to solve something that's in a denominator, it's a little bit stickier. That's why, you know, if you want to use the formula, use the formula. And then multiply that over, and you get the 0.25 times 1.96. And you could be approximating these along the way. And I'm going to keep showing you guys, this is how I solve it. I use the nice straight solving techniques. I tend to keep everything in decimal form to evaluate it all at once. But any method you want to use to solve that, as long as it's accurate, go for it. Fair? But that should give us some sample size, and a pretty comparatively small one. 9% margin of error is pretty big. 95% confidence level is pretty standard. I wouldn't expect this to be more than a couple hundred. But let's find out. 0.25 times 1.96 divided by 0.09 quantity squared. 118.5679012. So we need to sample a little bit more than 118 people. So we've got to survey 119 people.
That is the way I did, and I rounded just like you, but in the answer it will be like 120.
Well, let's see what it says. Oh, that changed the problem. There we go.
And I did the same with different
know.
problems.
I got 119.
That's weird. Well, the important thing is that I know how to do it.
Yeah.
Yeah.
And it can be, I mean, there's a lot of, and that's one of the reasons that as I go through here, you might notice, I don't approximate any of these until I put them all in at the end, right? This division squared is a pretty risky thing to approximate. Just because this is going to give you a pretty serious decimal, and anytime you square, you increase your approximation error a lot. So my guess is you're probably just not carrying quite the level of accuracy that's necessary to get exactly what this wants. Fair? But in some ways, because of that, it's really common. Like if somebody did this problem in practice, they would not go survey 119 people. They'd go survey like 125 or 150. You wouldn't round up to the nearest one. You'd likely round up to some nice bigger number that's not going to be too much more expensive, but that will make sure you have enough. But yeah, my guess would be that it's just in part of that approximation. And if that happens on things like tests, as long as I know the problems that are much more sensitive to approximation, and these sample size ones are always very sensitive. So if you're within a couple, I'm not going to get grouchy. The computer will go, no, and I'll go, yes, you're fine, because there's no way to not do this right at all and end up anywhere near a good value. If you're within a couple, you're just doing something with rounding. But that is a good reason to get used to carrying values around like this and approximating it all at once. In some ways, once you're used to doing it, it's actually easier. I mean, trying to calculate these as I go along and carry around those big decimals is frankly irritating. Once you're used to just moving them around like this, which takes practice, don't get me wrong, but it can actually become an easier way to do it. That seem reasonable? All right. Now, let's see. I grabbed one from 9.2 because I do want to talk about 9.2. Now, as always, as soon as we start kind of changing the language a little bit, 9.2 doesn't change the language a lot, but there are some distinctions. Things can get a little bit hairy, but I do want to make at least the argument that what we're doing in 9.2 is very, very similar conceptually to what we're doing in 9.1. So big fun word problem here, mostly fun because it has to do with chocolate chips, and who doesn't like chocolate chips, right? So this person wants to advertise how many chocolate chips are in each bag or big chip cookie at her bakery. She randomly selects a sample of 63 cookies. So as soon as we see that, n equals 63. And finds that the number of chocolate chip cookies or chocolate chips per cookie in the sample has a mean of 8.4. So the sample mean is 8.4. Oh, and we're even told a standard deviation. That's good. And a standard deviation of 3.4. Now, I'm going to stop there for a second and chat. If she wanted to advertise this, and she said each cookie has 8.4 or even just 8 chocolate chip cookies in them, and I guarantee that, if that's her advertising, she's going to be in trouble, because an average of 8.4 means half the cookies have more than 8.4 and about half the cookies have less than 8.4, right? So if she advertises that my cookies have 8.4 chocolate chips in them, or even just 8 chocolate chips in them, all those 7s and 6s are going to be her lying to her customers, right? So advertising 8.4 as an average would be a bad idea. Fair? So how much lower than 8.4 should she be looking at here? Well, that's what our confidence intervals are for. I want to be able to say that, you know, the average amount of chocolate chips that you'll get is in some range. And I want that range. I want to make sure that that range is really nice and accurate. Fair? So really, if you're going to advertise, you generally go with this lower number, because then you won't get sued as often. Now that might be pretty extreme for, you know, chips and chocolate chip cookies, but some people take their chocolate chip cookies very seriously. So how are we going to do this? Well, we want a 95% confidence interval. So we want a confidence interval. And we know how confidence intervals are built. And I really encourage you to start your confidence interval problems like this. We know our confidence intervals are an estimation plus or minus a margin of error, right? And that margin of error is found by taking a critical value and multiplying by a standard error. That's still true. That's always true. But this is a problem about means, not proportions anymore, right? So our estimation isn't a proportion anymore, isn't a p-hat. Our estimation is a mean. So instead of our estimation being a sample proportion, it's a sample mean. It's our x bar. Plus or minus. Our standard error, I'm going to skip over critical value here for just a second. Our standard error, well, it can't be that square root of PQ over N anymore because P and Q were proportions, right? This isn't a proportion problem. So we don't have any P's and Q's. But what was our standard error in 8.1? What was our standard error for means? It was standard deviation divided by the square root of the sample size, right? Now, again, talked about this. We don't know sigma. Sigma is the population standard deviation, right? We don't know the population standard deviation. So we have to instead use the sample standard deviation. Like we did in proportions. We used the sample proportion, not the true proportion. In proportions, we got away with that because it was close enough. In means, it's not quite close enough. So we have to compensate for that. And we compensate for this being S instead of sigma by using t-scores instead of z-scores. Fair? Now, what's a t-score? Z-scores, you certainly remember, z-scores are values on that curve, right? And you got your z-scores such that this was, 95%. Those z-scores were 1.96 negative and 1.96 positive, right? And how did we find those? Well, we found those in the way we started this class today, right? Using that nice normal distribution. The only difference between a z-score and a t-score is a t-score is based on a flatter, wider distribution. Your z distribution is the normal curve shape. Your t distribution is made to be flatter and wider, pushing those t values out, giving essentially more room for us to be wrong, more room for the error brought in by using that sample value instead of the true value. How much wider do we have to go? Depends on our sample size. The bigger sample, the less compensation we need. The smaller the sample, the more compensation we need. Luckily, we don't have to calculate that every time because we have a big, giant, fun chart. We have a t distribution chart. That t distribution chart is based on two things. This area in right tail, what does that mean? That's that amount of error we're looking for, right? How much area was in the right tail in David's problem, where we started today? Well, there were 2% in both tails, right? So 96% would have a tail error value of 2%. Fair? in a 95% confidence interval? How much is in that upper tail? But frankly, it's the same as how much is in the lower tail. How big are each of those tails? They're 2.5%, right? So we'd go to the t-distribution tail area of, where is it, 0.025. That 0.025 is 95% confidence level. Why is it listed in tail size as opposed to confidence level? Tradition. There is no reason for all of you not to take this page, print it out, and write 95% on top of that. And write 96% up here. Put in those confidence levels all the way across. Put the 90% here. Some of the tables even have them at the bottom. This one doesn't, but some of them even have it at the bottom. Fair? So that's the first thing we have to decide. What's our right tail area? What is our confidence level? You'll notice for that 0.025, that 2.5%, that 95% confidence level, if you go all the way down to the bottom of this chart, you see that 1.96. That 1.96 is the z-score we associate with 95%, right? It even says here, the z-score would be 0.196. And for a sample size of 1,000, we get really close to that. So the bigger the sample size, the closer you get to just the normal z-score. Fair? But the smaller the sample size, the bigger you need that distribution to be, all the way up to stupidly huge if your sample size is really small. But here's the problem. Here's an annoyance, again, based on history, based on tradition. Notice this chart does not say N or sample size, right? It says DF. DF is degrees of freedom. You probably don't remember, but we did talk about degrees of freedom before when we talked about finding standard deviation for a sample. Remember, we didn't divide by the sample size. We divided by one less than the sample size, right? We divided by n minus 1 when we found sample standard deviation. That's what these degrees of freedom are. So those degrees of freedom are one less than your sample size. So again, why not just replace this chart with an n and make those all bigger by 1? Hundreds of years of tradition. There's no reason to. You want to write next to that an n and put 2, 3, 4, 5, 6, go for it. Fair? The nice thing though is once you get used to reading these charts, you don't need to change that. So no one ever feels the need to change the charts. You know, it's one of those things. It's made to be easy to use, and it's easy to use in this form. It's not made to be easy to learn to use. So nobody goes, well, let's change how we write everything to make it easier for the students. Nobody likes to make things easier for students. That's not a priority, unfortunately. So it's never changed. Fair? But if you want to write those in while you're learning, go for it. So our degrees of freedom is, what was our sample size here? 63. So our degrees of freedom would be 62. So we would try to go to this chart as close to 62 as possible. Now notice as soon as we get past the 30s, it starts to make big jumps, right? That's because it starts to make the larger the sample size, the less difference it makes. So for 62, we're just going to use 60. Fair? whatever's closest on the chart. So 60, and we were over here at the 0.025 confidence level. Again, it's the one that goes with 1.96. Or if you prefer this 0.025 tail size, we're going to go down to 60. So 2.000, just 2. That's kind of nice.
I'm not quite sure with the 0.025. I can't understand it. Where you got it from?
Well, remember 95%, right?
Right.
95% means there's 5% that the tails include 5%, right?
Right.
So each tail is half of that. So each tail is 0.025.
Oh, okay. So it's basically the same than Z-score, but what changed is the table, right?
Right.
Okay. I was kind of lost.
Yeah, and it's weird, but it is exactly the same thing we did up here. It's just, the chart is listed by that tail size instead of being listed by the critical value. But you may remember the notation. Where did I write that? I thought I wrote it here somewhere. I know I did. There it was. That notation they give for the Z-scores is that Z alpha divided by 2.
Yes.
That alpha is the allowed error. So in a 95%, that allowed error is 5%, right? Divided by 2
Right.
is 0.025. So they've been kind of alluding to that tail size as we've gone along. And we've certainly used the tail size as we go along. It's just this is the first time the chart has been in terms of the tail size.
Right.
So that
Okay.
takes some getting used to. It does. It absolutely takes some getting used to. But once we're used to it, we're usually okay. And again, that degrees of freedom of 62 puts us in the 60s. So that's giving us this critical value of a nice even 2. And again, the nice thing is once you're used to doing this, that goes very fast. You just look it up on the table and it's 2.000. Our sample standard deviation was 3.4. Our sample size was 63. And our point estimate, our sample mean was 8.4. And that's our confidence interval. And you're right, that t-score is a lot like those Z's. We find it a lot like our Z's. They're just a little bit larger to account for the error in small sample sizes and by using that S instead of sigma.
I'm still a little confused on where you grabbed the 60 from on that chart.
Where or
Yeah.
why?
Like what? Yeah, why? Like what tells
Why?
you that?
So our sample size was 63, right?
Yeah.
And our degrees of freedom is 1 less than our sample size.
Oh, okay, that makes sense. I see.
The degrees of freedom here is 62.
I see. Thank you.
Sure. So yeah, that's why on the chart. Now, if there was a 62, we'd use it. But you can see there's not too much of a difference between 60 and 70, right? There's a little one. And if you used the calculator, and we'll talk about using the calculator for this later, it's in your text too. We could get a little bit more accuracy here, but very little. But when you're talking about the difference between 31 and 32, it's sometimes a little bit bigger. The difference between 8 and 9 is quite sizable. So the chart is broken up into smaller chunks until it's just like, okay, after a while, it's just, I don't want this chart to be 80 pages long, though I have seen T-score value tables that are very, very long that go from 1 to 100, one at a time. It's just a bigger table. And frankly, notice the difference between 1.962 and 1.960. Once you get much past a sample size of 1,000, just use the z-score. It's really useful for small sample sizes, all the way down to a sample size of 2. A sample size of 2 will give you more than 12 standard errors away from your sample mean. So that's going to be a huge interval. But if you're like, how big are asteroids? Well, how many asteroids have you seen? 2. How sure are you going to be about how big asteroids can be? You're going to want some range there, right? So it allows you to find a range for a high confidence level that has enough space in it. And that's, yeah, it's going to be huge. Ooh, we're over time. I'm late for my other class.
Me
But again,
too.
yeah, but again, that's the entire difference, is that the standard error formula is the old standard error formula. And instead of using those z-scores, we have to use those t's. That is the entire difference. So go play with that. And I'll see you later. I got to rush off to that other class.
Thank
But have a
you.
wonderful day.
Thank you.
Sure.
Happy
Thank you.
Thanksgiving.
Thank you.
Yes.
Say happy birthday.
Happy birthday.
Thank you.